Okay, so you should have already watched the 2 videos from Crash Course. Those will do a much better job of going over these different types of solids than I would be able to do on my whiteboard because they actually have a graphics team behind them. However, what I'll do is I'll go over the information just to really summarize it so that you know what I expect you to know. Good timing. Okay, first off, intermolecular forces. You should know these 4, and this time I'll put them in order of decreasing strength. So first, we have ionic bonding. Remember, this one is an exception because this is both an intermolecular force and an actual chemical bond. It's able to function in both ways. Let's give it a little star to say it's an exception. After that, we have hydrogen bonding. Keeping in mind that this is not a chemical bond. Hydrogen bonds are only intermolecular, okay? And then we have polar bonds, which are the same way. And then we have London dispersion forces. Hydrogen bonds happen between hydrogen and fluorine, oxygen and hydrogen, and nitrogen and hydrogen. Those are the only 3 times that we experience hydrogen bonding. Now, polar bonds will work with any other polar molecule that does not have these 3 bonds. London dispersion forces will happen in anything that doesn't have polar bonds, hydrogen bonds, or ionic bonds. This is basically everything else. For something like helium, helium to helium, this would be incredibly weak and would cause it to have an extremely low melting temperature and boiling temperature. However, in something like a lipid, which this is an example right here, I took a long time to build this because I wanted to. Oils like vegetable oil or canola oil, they all have this very interesting shape. I'll draw it on the board so that it's a little easier to see, but this has a ton of molecules in it. It is not polar. It still only functions by the London dispersion forces. Because of that, let's just set this guy right here. It still has these really weak interactions for each molecule, but because there's so many more molecules, that force is able to hold it together. Let's look at our different types of solids. Let's just give ourselves a little dividing line right here. First up, we have ionic solids. These are going to be brittle. They're able to dissolve very easily in a lot of different solvents. They are non-conductive until they are dissolved. Next, we have metallic. These bond based on the actual electrons being able to flow freely between metal atoms. So these metallic bonds are malleable because the electrons are still able to flow freely even if something moves, and they conduct both electricity and heat extremely well because these electrons that hold everything together are moving freely between the atoms. Okay? Next, we have network, covalent. That's going to be like these big structures like a coal or a diamond or a glass or a quartz crystal. These 3 will tend to have the higher melting points. After this, we're going to have a regular covalent. This would be something like water, which as a solid would be ice. So the water molecules will arrange themselves in order to be close together, but the thing driving that bond, keeping that solid together, is going to be those hydrogen bonds. It's not going to be a covalent bond, okay? And then we've got our atomic solids. And in this category, we're also going to include molecular. So I'm going to say atomic or molecular. What I'm really going to be saying here is that these stay together based on London dispersion forces. Okay? Covalent molecules stay together due to polar or hydrogen bonding. Network covalent stay together because of covalent bonds. So there is no intermolecular force in a network covalent. That's what makes them such strong bonds. This is going to be, and we're actually going to use a different color to say that this is not an intermolecular force. This is a regular covalent bond. Okay? The metallic bonding, again, this is not an intermolecular force. This is going to be metallic bonding. Maybe I'll make a video specifically about metallic bonding to get a little more in depth on that. And then ionic, let's use blue to say that ionic bonds can be both intermolecular and an actual chemical bond. We'll see really, that'll really become apparent as we look at dissolving and ionic bonds in the liquid state. So we'll say this is the ionic bond. Okay. The last thing we need to look at in this video right now is within that ionic bond. So keep in mind, when we melt or when we break something, like if I hit it with a hammer and it breaks, this is the bond that is being broken. This can really help explain why we have differing strengths, differing melting points, because it's going to be easier to break a London dispersion force than a covalent bond by a significant amount. So ionic bonds, what determines that melting point? It's really going to be, what we're really asking is, what affects the strength of an ionic bond? We have this specific trend on the periodic table of ionic radius. The radius is going to decrease this way. Decreases this way. Extra points if you can remember why. But so then I've got fluorine up here, fluorine, I've got sodium over here. Then let's use, what's that one? Cesium. Cesium down here. And then iodine down. So if I had something like sodium fluoride, which both have a charge of 1, versus cesium iodide, which still both have a charge of 1, because of this smaller ionic radius, the positive charge in here is going to be closer to the negative charge in here. Those atoms are able to get closer together. So there is a significantly stronger bond because of that. So this is much stronger. This is much weaker. Therefore, how would that melting point look? Well, the melting point would increase with that lowering of the ionic radius. Okay? The other factor, now let's look at this. NaF, that's a plus and a minus, versus, well, let's grab from a similar part of the table, let's go nitrogen. Nitrogen right here, and then let's do magnesium, sorry, figured it out. So magnesium and sodium have a very similar ionic radius. Nitrogen and fluorine are going to have a very similar ionic radius. However, magnesium nitride, remember nitrogen is going to have a -3 charge, magnesium is going to be a +2, so it's going to be a 3 and a 2. So this difference in charge is going to cause these to be together more strongly. And so my ionic strength will increase going this way. ionic strength goes up, so does my melting point. Okay. So, if you're looking at comparing melting points in ionic substances, which that's on this first page, then what you're going to be looking at is comparing the radius and the charge. If it looks like there's an even play, then it's kind of a give or take. And you should be able to look that up. You can Google that, what is this melting point? You should be able to see how much do these differences come into play. So go ahead and answer those questions. I'll attach a document linking to ionic radiuses. However, you should be able to figure out the ionic charges on your own. That should be basic information at this point. Okay, fantastic.